Hello everybody, welcome back. Today we're going to be looking at some interesting coordinate systems, or one interesting coordinate system, I suppose. So we're supposed to find ds squared, the scale vectors, the vector ds, the volume element, the a vectors, which are the basis vectors, and the e vectors, which are the unit vectors, for the parabolic cylinder coordinate system. And here are the equations that define the parabolic cylinder coordinate system. Uh, since you can see z equals z, for the most part, we can leave that alone. But we'll still take it through all the calculations and everything. If it's hard to visualize how this is going to work, just wait until the end of the video and I'll show you kind of what this looks like. So for the first thing, we're going to do these basically in order, because it's kind of laid out for us in an order that is beneficial. So to begin with, we're going to remember that our ds squared, ds being our arc length type of thing. So our ds squared um, is going to be our dx squared plus our dy squared plus our dz squared, not a subscript. Um, So if you take the square root on both sides of the equation, you just basically get the Pythagorean theorem. So uh, we're gonna need to find our dx, our dy, and our dz for these things, and square them. So our dx, um, so our dx is we need to take the derivative of both sides of the equation, or turn both sides of the equation into differentials, depending on what terminology you prefer. So when we take the derivative of this, um, it's going to be 2u, and then we need to chain out du. And same with this. This is going to be negative 2v dv. Since we're not doing the derivative with respect to really anything, we're definitely not doing it with respect to itself. Therefore, we need to have the extra du's in the situation, extra differentials. So u du minus v dv. And our dy is going to be something similar. We need to do the product rule. Remember from Calc 1. I've forgotten this and relearned it many times. Don't worry about it. So this is going to be, if we take the derivative, or if we take the differential of this one, it's going to be v du plus, and then do it the other way, u dv. So that's going to be v du plus u dv. Yeah, and we don't need any extra differentials since we have all of them there. And then our dz is just going to be dz, nice and easy. So then we need to square these because they're squared in our ds formula. So squaring this entire thing means we need to FOIL it out. So that means we have a u squared du squared, and then we have minus 2uv du dv. I'm kind of running into the space that I was going to write the other one in, that's fine. And then square the last term, plus v squared dv squared. And then for dy squared, we're going to need to FOIL it out again. So that is v squared, oh, excuse me, du squared, plus 2 times v, or actually just to keep it consistent, uv du dv, because when we multiply these by each other, we have 1v, 1u, 1du, 1dv, but we have to do it twice, so that's why there's a 2 in front of it, plus u squared dv squared, and our dz squared. is equal to dz squared. So now that we have these components, we can put them all in our formula. So that will mean that that this is actually equal to, and this is all to get this in terms of our new coordinate system. So we can get rid of all the dx's, the dy's, and the dz's. Well, not the dz's, but so that we can have it in terms of u, v, and z. So this is going to be this is going to be u squared du squared. And notice that when we add all these together, this part cancels out with that part. That's important because that makes things a lot easier to deal with for various reasons. So that's going to be plus v squared dv squared, and we're going to add v squared du squared plus u squared dv squared, and then plus our dz squared. So if we collect terms together, this is going to be equal to ds squared is equal to u squared plus v squared du squared plus u squared plus v squared dv squared plus dz squared. So this is our ds squared. So we have done this first part of the problem. To find the scale factors, it's as easy as taking the square root of the things in front of the different variables. So our scale factors can be read easily from here. Scale factors are square root of u squared dv, or u squared plus v squared. And then for our v variable, it's the same thing. U squared, square root of u squared plus v squared. And then for our dz squared, it is 1. So those are our scale factors. Nice and easy. You can cross another one off of our list. To find the vector ds, this is a vector now, not just a square or a something else. This is a vector ds. Vector. So the ds is going to be I dx plus j dy plus k dz. So we have everything we need to do this right now. We just need to substitute. So this is going to be u du minus v dv I plus v du plus u dv j plus k dz, or dzk, I guess, just to be consistent. Dzk. And it's going to be much more useful to us if we can write this in terms of our differentials, just like we did before. So we're going to do that. So what has a du part? ui and vj both have du parts. So ui plus vj both have du parts. What has dv parts? Negative vi and uj, which sounds very similar to what I just said, but it is actually the reverse, so don't get those mixed up. And uj dv And then what has a DZ part? K hat. See what I mean about how we can kind of ignore it? It's just tagging along for the ride, but it's not doing a ton, which is nice. Um, so we have found the vector ds. Um, so when our UMV variables change a little bit, that is the vector that shows the. So yeah, so when our UMV vectors change very small, very uh, tinily, um, then the point moves along the ds vector. Um, so I'll show that to you guys in a little bit. Um, so as far as finding the volume element is our d large V for volume instead of little v for variable. Um, so that is our it's our scale factors times our elements. So that's going to be square root of u squared plus v squared times square root of u squared times v squared times 1 times du times dv times dz. So that all condenses down to u squared plus v squared du dv dz. And that's our differential volume or our differential volume. Uh, so yeah, when these change a little bit, that's how the volume enclosed by this little volume here would change. That doesn't make very much sense until you see it. So that's all we'll say about that for now. So we found the volume element. Nice. Now we need to find the A vectors, the basis vectors. You can actually just read them off from the ds formula. So that's what we'll do. Our AU is just what is in front of our du there. So it's ui plus vj. And then our, no, not d, our AV is negative vi plus uj. And then our AZ is equal to k. So those are our A vectors. And our E vectors, our unit vectors that make up this whole thing. You can, if you do some analysis, you can see that these two are always going to be 90 degrees apart. That's not a coincidence. They're also 90 degrees apart from this. This is a orthogonal vector system, or yeah. So these are kind of like you can think of them as like coordinate directions, but they change based on the values of the variables. So we'll get to that in a little bit here. So our E vectors, the last thing we have to do here, these are our unit vectors. So they're just our A vectors divided by our scale factors, which means that it's ui plus vj over square root u squared plus v squared. This is EV. This is negative VI plus UJ over square root of U squared plus V squared. And this is just the same. It's also K hat. But you also probably knew that already because this is a unit vector here, so it's not going to change anything. So yeah, So these are all unit vectors now. So now you can really think of them as coordinate directions. So yeah, uh, it's difficult to explain any more than that without actually being able to see it. So now that this whole problem is done, we'll go ahead and take a look at what this actually means. Let's see. Okay, let's take a look here. So here we have our whole system. So in a normal coordinate system, you have, or in a rectangular coordinate system. Also, this is two-dimensional. We're ignoring z since it would just be a different layer into or out of the screen, and it would look the same. Um, so uh, in a rectangular coordinate system, you have vertical lines that represent the x, and a vertical line, y can be anything, and x is fixed. Similarly, you have horizontal lines where y is fixed and x can be anything. So that's what these parabolas are here. The red parabola is with it's with v fixed and u is varying. Is that right? I think it is. Yeah. Um, so uh, so I'm changing u. Yeah. So it's with v fixed and u varying. So I'm changing u, and that is allowing me to so that's moving me along the temporary v constant line. And then same with this here. This is with v varying and u fixed. So u is staying put, and I'm moving along the u constant line. So you can see when I'm moving, yeah, so okay, so when I'm moving v, or when I'm moving u, my bad, the direction that I go, so like when I move one tick, the direction that I move is actually the same direction from 0 to this this EU. So one little tick, I'm moving in that direction. It's also the same direction as AU, but these are scaled because of the properties that we found a little bit ago. So same here. When I move this one tick positive, obviously, if you move one tick negative, it's the opposite direction. So when I move one tick positive, or when I move one tick positive, I move in the direction that these are facing in, and I move roughly the amount shown by the a vector. So like you can see when I'm not moving a whole lot. Here, I'll even make it smaller. Not too small. So I'm not moving a whole lot between steps here. You can see that the a vector is relatively small, but when I go out here, I'm moving a lot more per tick, and the a vector is relatively bigger. So, um, all in all, this is a rough thing to visualize. Um, I didn't really understand pretty much anything about what was going on here until I made this demonstration here. There's all sorts of interesting properties about this. So like if I go negative on the U and then go negative on the V, it brings me back to the same spot as where I was. You can kind of predict that would happen by looking at the coordinates or the definitions of these variables. There's also some interesting properties with this and the Laplacian operator. So these are things that you conceivably could use to solve some difficult equations. So now you know how to find various properties of these and what you can do with them. So thank you very much for watching.